Fablab, che è l'hangout on air, che direttamente registra, filma e poi alla fine pubblica. Non devo fare nessun divertimento.
Nel minuto che si vuole
Esatto.
se la passi
Ragazzi, ci stai Costa? Dimmi tu via.
vai.
Ok, wow, siamo on air. Allora, grazie di essere qui. Siamo arrivati, per chi c'era, alcune delle facce le riconosco che c'erano la volta scorsa quando abbiamo fatto, diciamo, all'inizio la presentazione di questo percorso del programma Maker in Residency. Per chi non c'era, qui a WeMake facciamo ogni 8 mesi, ospitiamo degli artisti maker o designer su un progetto specifico per lavorare insieme a noi su una tematica particolare. Questa volta abbiamo invitato Afroditi Psarra dalla Grecia, che è venuta con noi, che è venuta a WeMake, la conoscevamo già da un paio d'anni per il suo lavoro intorno al mondo dei wearable e della musica elettronica. Ha portato con sé Dafni, che ha lavorato in Papadopoulou, che ha lavorato con lei a questo progetto, in modo particolare per la parte di diciamo, progettazione parametrica delle maniche, ma adesso vi racconteranno tutto. Siamo molto, diciamo, soddisfatti, il progetto è molto bene, adesso ve lo racconteranno nei dettagli. E grazie di essere state qui con noi e lascio la parola a loro. In inglese, ovviamente.
So thank you all very much for coming. My name is Afroditi Psarra. I'm a Greek media artist working with textiles, electronics and sound. And I also would like to thank Zoe for inviting us to do this 2-week residency here. We were together with Dafni Papadopoulou. I'm an architect, and we met with Afroditi when I attended one of her workshops, and she's the one who introduced me to electronic textiles. So we came together here to do this 2-week residency to develop a project called the Culture Garment. So this opportunity to come here offered us new ways of collaboration, and we decided to work on a series of wearables that combine the electronic handicrafts and soft circuits with digital fabrication techniques and parametric design. And we really hope that this project is the start for an ongoing research that will continue on, and maybe on the next occasion we could come here and do this project. So the conceptual background. This project was inspired by a series of books written by Scottish science fiction writer Ian Banks, where in his culture series he talks about an advanced future civilization of humans that live together with machines in a world where everything is sentient. So everything is kind of alive in a sense. So this gave us the inspiration to create a wearable that would somehow visualize the user's interior workings. So we came up with this idea. This is our concept sketch with a dress that incorporates a wearable microcontroller and uses parametric design and digital fabrication on the sleeves of the garment. And the sleeves, the idea was that the sleeves would move accordingly to the wearer's heartbeat. So that we will talk a little bit about the design and fabrication of the sleeves. So in order to design the sleeves, which have this structure that you can see, we use the software that is called Grasshopper. And Grasshopper for parametric design. So I'm not going to get into many details, but for those of you who are not familiar with parametric design, the general idea is that you design the process that generates a geometry and not the object itself. So this is the definition for the creation of this structure. I forgot to mention that Grasshopper is free software and open source, meaning that people exchange ideas and create a community. So in this case, this is a picture that explains how the structure was created. We started by drawing only the surface of the sleeve, the base surface, which is created by lofting these curves. Then we divide the surface in two directions. We scale the pieces that are produced by this subdivision, and then we extrude all the scaled shapes towards one point. So this is how this structure is created. So in this case, for example, the same procedure with the definition that you saw before can be applied into a different surface and produce different result, but the same logic. Also, Grasshopper is very good for analyzing geometries and therefore preparing them for digital fabrication. So here we have the opportunity to use the laser cutters of WeMake. This is the definition for unfolding each one of these pyramids and preparing them for laser cutting. So what we did was to number with the two-digit number. The first digit is the number of the line that it belongs to, and the second digit is the number of the piece itself. So Grasshopper allows to do the unfolding not for each piece one by one, but with an automated procedure that is applied to all of them. And so at the picture at the right, you can see the final result, which allowed us to cut all these pieces with a laser cutter with an automated procedure. So these are the pieces that we created with the laser cutter, and we folded them one by one, and we connected them all together, following the numbering logic that I showed you before. So the idea that we had is that we had to find a mechanism to create movement on the sleeves. So we had initially two ideas. One was to use a servo motor, but then a servo motor would be quite noisy, and the second idea was to use muscle wire. So I will explain a bit later about all the details on how we created the muscle wire actuators, but the idea is that for the shirt that you see here, we are using a Lillipad Arduino USB microcontroller, and then we have two muscle wire actuators, one connected in each sleeve, and we're using a tip 122 Darlington transistor as a digital switch to turn the actuators on and off. So, and another thing is that the muscle wire actuators consume a lot of current, so we need to supply them with a separate battery for each one. Also, if you notice the schematic, you will see that we're using 20 centimeters of this specific muscle wire because the muscle wire is really sensitive in a way, and you have to calculate from the start how much voltage and how much current you're going to give it to contract. So in this case, we're using a 3.7 LiPo battery that runs at 1,000 milliamperes per hour. And this allows us actually to have the muscle contracting for approximately 10 minutes. So you can see that the current consumption is quite high. This is the second schematic for the dress, which is, the circuit is quite a lot more complicated because we have 6 muscle wire actuators, and we also have the pulse sensor connected that controls the turning on and off of the actuators. But the idea is also the same, that you need a separate battery to power each actuator. And in this case, we're using an Arduino Pro Mini microcontroller because the pulse sensor we have used needs also a 5-volt battery and needs to run at 16 megahertz. So here I'm going to show you some images of the muscle wire actuators that we created. So the basic idea is that the muscle wire flexinol, the one we've used, is a mixture of titanium and nickel, and it has a specific property that at certain temperature it can contract. It means that it can lose 10% of its length, and also it has a point where you can hit the wire to create a shape that is going to stay in its memory. So every time you hit it at less temperature than when you train it, the wire contracts in the shape that you have given it. So in this case, we created, we trained them as springs. And we created a handmade actuator made from a PVC stripe that is covered on Kapton tape that can hold to very high temperature. And we have soldered using jewelry bits because the muscle wire cannot be soldered. We have soldered the muscle wire on a piece of copper tape and then connected it with normal wire. And you can see that from the photos that here the muscle wire is not, it is off, so there's no current and power passing through it. And then with the help of a battery, we're heating it up so it starts to contract and return to its original shape, which is this one. We can actually show you a very quick video about it as well. So it's this one. And we had to create this kind of mechanism because, of course, the muscle wire contracts when it's heated, but then when it cools down, it doesn't have the strength to return to the previous shape. So we had to find a mechanism that could push it down in order to return to its shape. And here you can see how we attach the muscle wire underneath our leather structure. So this process, of course, needed a lot of testing. Here you can see some photos during the last week that we have been working here intensively. And I would like to finish off with the soft circuit part of the garment and all the actual handiwork that was being done in order to produce the circuit, because the initial idea, as I mentioned in the start, was to combine digital fabrication processes with electronic handicrafts. So here you can see that each connection is hand-sewn and hand-stitched in a chain stitch using copper conductive thread, which is actually solderable. Here you can see some details of the finished circuit. This is actually where the pulse sensor connects to the dress. You can see it close afterwards, because the pulse sensor is an earring that is incorporated to the dress. So we would like to thank all the people that we made for your help and support during these 2 weeks that we have been here. And some funny photos from our time here. And we've already have the project on GitHub, so you can follow this link if you want to follow the development of the project. And thank you very much. Come closer to actually see how the...
Think about the question, se avete domande, vediamo una funzione adesso.
And you can see the circuit from close. So the dress is not finished yet, so it's not functional, but it will be finished soon, but we have the shirt that is functional.
Maybe you can show it on the side, you can show it. Sembra che respiri.
How much temperature?
How much?
Temperature.
So for these specific actuators, we made them with low temperature muscle wire, which is heated at 70 degrees. But from the testing that we did, we didn't have to put some kind of under fabric in this one, so it's not burning the fabric. The heating is contained. Huh?
Not the fabric, not the
There is a fabric underneath the skin. So there is fabric between the actuator and the skin, so it's isolated.
Yeah, does it depend also by the ambient environment?
No, because it really needs at least 70 degrees to make the contraction. So it doesn't depend. I mean, 70 degrees is not a temperature that you could reach.
Another technical question.
Yes.
Can you control in some way the speed of the contraction?
Yes, because it has, if you go on the datasheet of its muscle wire, for example, for this one, it needs 1050 milliamperes for 1 second contraction. So you can calculate and give it less amperage to have a minor contraction, if you wish. But this is the maximum.
It's not a transition point like that. Is pure.
Yeah.
Proportional, the contraction is
Yeah.
proportional around the temperature, but
Also the amperage.
So the autonomy of this battery is that means
For the ones that we're using, actually these are for 12 minutes, but you can always use batteries in series, so they will increase the time. And also if you want to use it for something that is not wearable, for something, for example, for interior design or some kind of application, you can always use a transformer.
okay.
So you have steady current all the time passing through the circuit. You can have also an expanding circuit. What's